In module 3, we have seen the proofs of various recurrence relations along with the applications. We now move to module 4. In module 4, we look into the orthogonal properties of Legendre polynomials. The orthogonal property is another important aspect of Legendre polynomial. We do the proof explicitly along with some very good examples. After that, we will move to Rodrigues formula. Rodrigues formula is used to generate Legendre's polynomial without the help of recurrence relations. It is again another very important formula which needs to be reminded again and again. Orthogonal properties of Legendre's polynomial. If Pmx and Pnx are Legendre's polynomial, P and m and n being positive integers, then integration -1 to +1 Pmx Pnx is equal to 0 if m not equal to n and is equal to 2 by 2n plus 1 if m equal to n. In case 1, we take the proof when m is not equal to n. Since Pmx and Pnx are Legendre's polynomial, they are going to satisfy Legendre's equation, and hence we get equation number 1 and equation number 2. We next multiply 1 by Pnx and 2 by Pmx, and then subtracting we obtain the expression number 3, which is 1 minus x square Pn into P double dash m minus Pn into P double dash n minus 2x Pn P dash m minus P dash n Pm plus m into n plus 1 minus n into n plus 1 Pn Pm equal to 0, given by equation number 3. After simplification, we get expression number 4, where we have only expressed ddx in terms of the double derivative. After simplification, we get the equation number 5, which is ddx of 1 minus x square Pn P dash m minus Pm P dash n is equal to n minus m n plus m plus 1 Pn Pm. We now integrate both sides with respect to x from -1 to +1, and we get n minus m n plus m plus 1 integration -1 to +1 Pmx Pnx dx is equal to 1 minus x square into Pn P dash m minus Pm P dash n, the values to be calculated from x equal to -1 to x equal to +1. Since n is not equal to m, we will have this integration is equal to 0, and hence this is the proof for case 1 when n is not equal to m. We next go to case 2 where m is equal to n. We need to prove the result -1 to +1 Pnx whole square dx is equal to 2 by 2n plus 1. Please recall the generating function for Legendre's polynomial, which is given by expression number 8, which is true for n. Replacing n by m, we get expression number 9, which is same as 8, where your n is replaced by m. We now multiply expression 8 and expression 9 to get the expression number 10, which is 1 minus 2xz plus z square whole to the power -1 is equal to summation m equal to 0 to infinity summation n equal to 0 to infinity Pmx z to the power n plus m Pnx. We now integrate both sides with respect to x from -1 to +1 and get integration -1 to +1 1 minus 2xz plus z square whole to the power -1 dx equal to summation m equal to 0 to infinity n equal to 0 to infinity -1 to +1 Pmx Pnx dx z to the power m plus n. Since m is equal to n in this case, we will get the expression here to be summation n equal to 0 to infinity -1 to +1 Pnx whole square dx z to the power 2n is equal to, we now have to integrate the expression dx by 1 plus z square minus 2 xz from -1 to +1 since m is equal to n. And if you do that, you will get the expression number 13 between -1 to +1, and if you calculate that value, you will be getting -1 by 2z 2 log of 1 minus z minus 2 log 1 plus z, given by equation number 15. We now use the series formula of log 1 plus z and log 1 minus z. If you do that, you will be getting the expansion to be z minus z square by 2 plus z cube by 3 minus dot 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 minus z square by 2 minus z cube by 3 minus dot dot dot. And if you simplify that, you will be getting equation number 17. Therefore, we get summation n equal to 0 to infinity -1 to +1 p n x whole square dx z to the power n is equal to 2 times summation z to the power 2n divided by 2n plus 1. We next equate the coefficient of z to the power n from both sides, and if you do that, you will get the result -1 to +1 p n x whole square dx is equal to 2 times 2n plus 1. And this completes the proof of the orthogonal properties of Legendre's polynomial when m is equal to n. We now look into a few examples about this orthogonal property. The first example, we have to show that integration -1 to +1 x pn minus 1 x dx is 2n divided by 4n square minus 1. Please recall the recurrence relation from module 3, recurrence relation 1, which says that n plus 1 p n plus 1 x is equal to 2n plus 1 x p n x minus n minus 1 p n minus 1, which we can put in the form of equation 19, that is x p n x is equal to n plus 1 divided by 2n plus 1 p n plus 1 x plus n by 2n plus 1 p n minus 1 x. We now multiply both sides of 19 by p n minus 1 x and then integrating with respect to x from -1 to +1, and we obtain integration -1 to +1 x p n x p n minus 1 x dx is equal to n plus 1 divided by 2n plus 1 integration from -1 to +1 p n plus 1 x p n minus 1 x dx plus n by 2n plus 1 integration from -1 to +1 p n minus 1 x whole square dx. Please note, if we use the orthogonal property which says that if m is not equal to n, we have the integration to be 0, and if n is equal to n, we have the integration to be 2 divided by 2n plus 1. If we use the property here, we see that this n and n plus minus 1 is different, and hence the value is 0. Again, here n plus 1 and n minus 1 is different, so the value is 0. But here both p n minus 1 and p n minus 1, they were same, and hence the value will be 2 divided by 2 times n minus 1 plus 1, which is given here. After simplification, we get the result 2n divided by 4n square minus 1. This concludes the example 1. In example 2, we have to show that integration from -1 to +1 x square p n plus 1 x into p n minus 1 x dx is equal to 2n into n plus 1 divided by 2n minus 1, 2n plus 1, 2n plus 3. And from there, we have to deduce the value 0 to 1 x square p n plus 1 x into p n minus 1 x dx. Again, please recall recurrence relation 1 from module 3, which says that n plus 1 p n plus 1 is equal to 2n plus 1 x p n minus n p n minus 1, which implies 2n plus 1 x p n is equal to n plus 1 p n plus 1 plus n times p n minus 1. We next replace n by n minus 1 and n plus 1 in 20. which is this particular expression. And if you do that, we get 2n minus 1 x p n minus 1 equal to n p n plus n minus 1 p n minus 2 given by equation 21, and 2n plus 3 x p n plus 1 is equal to n plus 2 p n plus 2 plus n plus 1 p n, which is equation number 22. We next multiply 21 and 22, and if you do that, on the left hand side you will be getting 2n minus 1 2n plus 3 x square p n minus 1 p n plus 1, and on the right hand side we will be getting 4 terms if you multiply these two, which is given by equation number 23. We next integrate equation number 23 from minus 1 to plus 1 and use the orthogonal property of Legendre's polynomial. And if you do that, please note that this n plus 2 and n are different, n minus 2 n plus 2 are different, n minus 2 p n are different. Hence, when you integrate this from minus 1 to plus 1, all these expressions will be 0 and you are only left with this one term only, which gives you n into n plus 1 2 divided by 2n plus 1, and hence we get the result integration from minus 1 to plus 1 x square p n plus 1 x p n minus 1 x dx is equal to 2n into n plus 1 divided by 2n minus 1 2n plus 1 2n plus 3. For the second part of the problem, we note that this p n x is a polynomial of degree n, and hence x square p n minus 1 x p n plus 1 x is a polynomial of degree 2, which comes from here, n minus 1 which comes from here, and n plus 1 which comes from here. So, overall if we add all these degrees, it is coming to 2 times n plus 1, which is an even number, and hence x square p n minus 1 p n plus 1 is an even function of x, which implies that integration from minus 1 to plus 1 x square p n minus 1 x p n plus 1 x will be equal to 2 times 0 to 1 x square p n minus 1 x p n plus 1 x dx. And as proved before, this value is equal to n into n plus 1 divided by 2n minus 1 2n plus 1 2n plus 3 given by equation number 27. We can multiply this 2n minus 1 and 2n plus 1 to make it 4n square minus 1, which is the desired result. Our next example, we have to prove that 2n plus 1 into x square minus 1 p dash x is equal to n into n plus 1 p n plus 1 plus p n minus 1, and from there we have to deduce integration minus 1 to plus 1 x square minus 1 into p n plus 1 x into p dash n dx. From module 3, please recall recurrence relation 5, which gives x square minus 1 p dash n x is equal to n x p n x minus p n minus 1 x given by equation 29. Recurrence relation 6 from module 3 gives x square minus 1 p dash n equal to n plus 1 p n plus 1 x minus x p n x. We multiply equation 29 by n plus 1 and 30 by n, and adding we get n plus 1 into x square minus 1 p dash n plus n into x square minus 1 p dash n is equal to n plus 1 n into x p n minus p n minus 1 plus n into n plus 1 p n plus 1 minus x p n. If you simplify that, you will arrive to equation number 32, which says that x square minus 1 p n x p dash n x is equal to n into n plus 1 divided by 2n plus 1 Pn plus 1 plus Pn minus 1. We now multiply both sides of 32 by Pn plus 1, and next we integrate with respect to x from minus 1 to plus 1, and we get integration minus 1 to plus 1 x square minus 1 Pn plus 1 into P dash n dx is equal to n into n plus 1 divided by 2n plus 1 integration minus 1 to plus 1 Pn plus 1 x into Pn plus 1 plus Pn minus 1 dx. If you now multiply, you will get integration minus 1 to plus 1 Pn plus 1 square and integration minus 1 to plus 1 Pn plus 1 into Pn minus 1. Like before, if we use the orthogonal property, we will see that since Pn plus 1 and Pn minus 1 are different, this value is going to be 0, whereas we get a value 2 divided by 2 into n plus 1 in this case. Hence, we get the result from minus 1 to plus 1 x square minus 1 Pn plus 1 x P dash nx dx is equal to n into n plus 1 divided by 2n plus 1 multiplied by 2 divided by 2 into n plus 1 minus 0, which after simplification gives 2n into n plus 1 divided by 2n plus 1 into 2n plus 3, which is our desired result in example 3. We have just learned about the orthogonal property of the Legendre's polynomial. We have also seen some very good examples, and I hope they are clear to you. We next move to Rodrigues formula, which is another important aspect of Legendre's polynomial. With the help of Rodrigues formula, you will be able to calculate the Legendre's polynomial without the help of recurrence relation. Let us see how we do that. Rodrigues formula. In 1878, Heinrich Edward Hein introduced the name Rodrigues formula after it was pointed out by Hermite that in 1865 that Rodrigues was the first to discover it. Instead of solving the recurrence relation, one can obtain the coefficients in Legendre's polynomial independently using Rodrigues formula, and this is given by Pnx is equal to 1 by 2 to the power n factorial dn dxn, that is the nth derivative of x square minus 1 whole to the power n. Let us look into the proof of this formula. From the definition of Legendre's polynomial, we get Pnx is equal to summation n equal to 0 to n by 2, which is defined as n by 2 if n is even and n minus 1 by 2 if n is odd, minus 1 whole to the power r 2n minus 2r factorial x to the power 2n minus 2r divided by 2 to the power n factorial n minus r factorial n minus 2r factorial. We use the binomial expansion of x square minus 1 whole to the power n, which is equal to summation r equal to 0 to n ncr x square to the power n minus r minus 1 whole to the power r, which we can simplify as ncr x to the power 2n minus 2r minus 1 whole to the power r. We now take the right hand side of the formula, that is 1 by 2 to the power n factorial nth derivative of n square minus 1 whole to the power n, where we replace n square minus 1 whole to the power n by expression number 35. And if you do that, you will be getting 1 by 2 to the power n factorial summation r equal to 0 to n ncr minus 1 whole to the power r nth derivative of x to the power 2n minus r. Please note that the nth derivative of x to the power m is equal to 0 if m is less than n, and is equal to m factorial divided by m minus n factorial x to the power m minus n if m is greater or equal to n. Therefore, the nth derivative of x to the power 2n minus 2r is 0 if 2n minus 2r is less than n, that is r is greater than n by 2. Therefore, we replace summation r equal to 0 to n by summation r equal to 0 to n by 2 if n is even, and by summation r equal to 0 to n minus 1 by 2 if n is odd. In short, we replace summation r equal to 0 to n by summation r equal to 0 to box n by 2, and we obtain 1 by 2 to the power n into n factorial nth derivative of x square minus 1 whole to the power n is equal to 1 by 2 to the power n into n factorial summation r equal to 0 to n by 2 is equal to minus 1 whole to the power r ncr nth derivative of x to the power 2n minus r. And by using the equation 36, we come to the expression summation r equal to 0 to n by 2 1 by 2 to the power n into n factorial multiplied by n factorial minus 1 whole to the power r into 2n in minus 2r factorial divided by n minus r factorial n minus 2r factorial x to the power n minus 2r. And if you recall, this is by definition the Legendre's polynomial of degree n, which we get by using 34, and this completes the proof for Rodrigues formula. We now see by using Rodrigues formula how we can calculate the Legendre polynomials, namely say p0x, p1x, p2x and p3x. The Rodrigues formula is given by equation number 37. If you now put n equal to 0, you will get 1 by 2 to the power 0 by 0 factorial x square minus 1 whole to the power 0, which is equal to 1, that is p0x equal to 1, which we have already derived previously. p1x is equal to 1 by 2 to the power 1 by 1 factorial the first derivative of x square minus 1, which is simplified to x, given by equation number 39. Similarly, equation number 40 shows the derivation of p2x, which is equal to half of 3x square minus 1. For p3x, we substitute n equal to 3 in the Rodrigues formula, and we get the value is equal to half of 5x cube minus 3x. Likewise, you can calculate p4x, p5x and so on. Next, we take a very good example where we have to show using Rodrigues formula integration minus 1 to plus 1 x to the power m p n x is equal to 0 if m is less than n, and minus 1 to plus 1 x to the power n p n x is equal to gamma function half gamma function n plus 1 divided by 2 to the power n gamma function n plus 3 by 2, which is equal to 2 to the power n plus 1 factorial n whole square divided by 2n plus 1 factorial if m is equal to n. So, the case 1 where we take m is less than n, the Rodrigues formula is given by p n x equal to 1 by 2 to the power n n factorial nth derivative of x square minus 1 whole to the power n. We take the left hand side from minus 1 to plus 1 x to the power m p n x and substitute this p n x by the Rodrigues formula. If you do that, you will be getting 1 by 2 to the power n into n factorial integration from minus 1 to plus 1 x to the power m nth derivative of n square minus 1 whole to the power n dx. Integrating by parts, we get equation number 42. Let us now simplify the expression nth derivative of x square minus 1 whole to the power n, which we can write as nth derivative of n minus 1th derivative of x minus 1 into n plus 1. We use Leibniz theorem and we get the result to be n factorial into x minus 1 into x plus 1 whole to the power n plus dot 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 the n factorial x plus 1 into x minus 1 whole to the power n. The limit goes from minus 1 to plus 1, and this value is 0 if you substitute x equal to plus 1 or x equal to minus 1, and hence we get integration from minus 1 to plus 1 x to the power m p n x is equal to minus 1 whole to the power 1 m divided by 2 to the power n m factorial integration from minus 1 to plus 1 x to the power m minus 1 n minus 1th derivative of x square minus 1 whole to the power n dx, given by equation number 44. If you continue the process, you will be arriving at equation number 45, which is minus 1 whole to the power 2 m into m minus 1 divided by 2 to the power n factorial multiplied by the given integration. We continue this till m times, and you will be getting minus 1 whole to the power m into m factorial divided by 2 to the power n into n factorial integration from minus 1 to plus 1 ddx of the n minus m minus 1th derivative of x square minus 1 whole to the power n. If you integrate it from minus 1 to plus 1, we arrive at equation number 48, which after simplification gives equation 49 gives minus 1 whole to the power m into n factorial divided by 2 to the power n into n factorial the n minus m minus 1th derivative of x minus 1 whole to the power n x plus 1 whole to the power n from minus 1 to plus 1, and if you put both the values, the answer is 0, and this proves the first part of the problem. In the second part, we consider when m is equal to n, and if you do that, you will be getting from minus 1 to plus 1 x to the power m p n x is equal to, we use the same Rodrigues formula, which is 1 by 2 to the power n into n factorial x to the power m nth derivative of x square minus 1 whole to the power m dx. We use the same technique as we used in the first half of the problem, and if you do that, you will be deriving equation number 53, which is minus 1 whole to the power n into n factorial divided by 2 to the power n into n factorial integration from minus 1 to plus 1 x to the power n minus n the 0th derivative of x square minus 1 whole to the power n dx. If you simplify, you will be getting minus 1 whole to the power n divided by 2 to the power n integration from minus 1 to plus 1 x square minus 1 whole to the power n. Now, to do this integration, we substitute x equal to sin theta, whose derivative is cos theta d theta. You substitute this value and you get equation number 57, which is 1 by 2 to the power n minus 1 integration 0 to pi by 2 cos of 2 n plus 1 theta d theta. Please recall the formula for gamma function, and if you use that, you will be getting equation number 58, which is 1 by 2 to the power n minus 1 gamma function n plus 1 gamma half divided by 2 times gamma function 2n plus 3 divided by 2. If you simplify that, you will be getting equation number 59, which is n factorial by 2 to the power n 2 to the power n plus 1 divided by n plus 1 2n minus 1 dot 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 3 1. We next multiply both numerator and denominator by 2 4 6 8 dot dot 2n minus 2 2n, and if you do that, you will be arriving at equation number 61, which is 2 into n factorial multiplied by 2 into n minus 1 dot dot 2 into 2 2 into 1. We take 2 common from each of the terms, and you will be arriving at equation number 62, which is 2 into n factorial 2 to the power n into n factorial divided by 2n plus 1 factorial, which after simplification gives 2 to the power n plus 1 into n factorial square divided by 2n plus 1 factorial, which is our desired result. So, in module 4, we have learned about the orthogonal property of Legendre's polynomial, supported by the proof and some very good examples. Next, we move into Rodrigues formula, which is another important aspect of Legendre's polynomial. We have also given the proof of Rodrigues formula along with some examples. In module 5, we will take up Legendre's function of second kind. We will look into its properties, the recurrence relation, and its application. Thank you.